Hi everyone, are you able to hear me and see my screen clearly? Let me just check the audio. All right, great, great. So, hi Abhinav, hi Balaji, hi Bintao, hi Kamal, hi Nirav, hi Noor. Yes, good morning and a very happy new year. Great, great to have all of you in the session. All right. All right, so before we start, there's a question from Bintao. Course materials are available for until the topic 3. Could CloudX Lab upload the material for rest of the topics? So that will happen by the weekend. I mean, it'll take us a couple of more days to do that. And moreover, could you also post the project this weekend? Sure, sure. Sharing you, we'll be sharing with you the project soon. All right. So Noor is not able to hear. All right. Great. Great. All right. So should we start? Sure. Great. Great. So far, what we have learned is that what we learned till the last session is that we we were basically finalizing our model. So we learned very important things till the last session, and these whatever we are learning as this part of this end-to-end project is going to be very useful. Okay, so we learned something called cross-validation. So cross-validation, and we found that the as part of it, we also learned that random forest random forest is performing better than decision tree or linear regression. Okay, so this is what we learned in the last session, and we also learned a few more things that we are going to talk. A question from Nirav: when will the grouping done for the project work? That will happen probably this week itself. Okay, so that will happen this week itself. Okay, because end-to-end project will finish today, and and then we will be after that we'll be sending you after this weekend we'll be sending you the we'll be pairing up, and that way it'll be good. Okay, all right. So all right, so let's start. So till the last session, what we have learned is that random forest was performing great. We had checked with our the let me go back. Let me go back a bit. Yeah. So we had checked with the K-fold using K-fold techniques. In K-fold, what we do is we break our data set into K parts, and in K number of iterations, we we test against each of the k part. So we test against first, train against rest of it, and so on. So first we train on the rest of the parts and test on the first one, then second one, then third one. So we learned that using cross-validation technique, using k-fold cross-validation technique, we were able to we were able to compare the algorithm very well. And we found that the random forest one is performing far better because the root mean square error is the lowest in case of random forest, as well as the precision was better because the standard deviation was smaller. Okay, so this is what we learned till the last time. Now we afterwards we talked about fine-tuning your model. So I hope everybody's okay till now. Okay. So Gopi is okay, Nirav is okay, Kamal is okay. All right. All right. Great, great. So far, everybody's okay with this. Now, then we talked about fine-tuning the model, and in the fine-tuning, what we did was basically one of the attempts that we did was using the one of the things that we learned till the last point was using the hyperparameter optimization. So all we did was tweak the various parameters to various algorithms, even though we knew nothing about the hyperparameter, we knew nothing about the arguments that we had to pass to the functions or the algorithms, even though we were able to optimize upon it. And the approach was very much like a brute force. Brute force as in we were trying all possibilities. Okay, so we were trying all possibilities. So, so using grid search, what we did was we created the various combinations of the parameters. So this was first set, this was second set. We tried with this argument having all of these values one at a time, and then we tried this one at a time. So basically all permutations of n estimators and max features, and then the second set and so on. This way by going over all of these and running the algorithm that many times with all the combinations, we were able to figure out which parameters are great. Okay. All right. So that's what I'm saying. So even though we knew nothing about these parameters like bootstrap and others, still we were able to iterate over all of these. Okay. So these are the parameters of our algorithm. All right. So basically the idea was that we will try all possible arguments to the functions and see which one is performing better. So instead of rewriting the for loop, we use the grid search function. All right. And and that's what we did here. All right. And we figured out that max features 8 and an estimator 30. We don't know what are these right now. We will talk about these in more details when we study the random forest. So the output is showing that these are the arguments which performed best. Okay. All right. So when we in our algorithm, like in the grid search, the best estimator was random forest with these arguments. All right. Now, then we printed the output here. Okay, so let me go back to, I think this is not a good idea. I'll just take it out and all right. So great. And let me go back to my notebook. All right. So a question from Bintao is that how grid search can fine-tune models. Okay. So basically, we don't know what are the arguments right now to random forest regression, right? We figured out that random forest one is performing the best, and we wanted to further figure out what arguments to random forest regressor are the best. So what we did was we created a list of arguments that we should try, and we tried all of those. And that's what grid search did for us. Grid search tried all possible arguments which we have given here, So it tried 3, 2, and so on. And that's it. That is visible here. You can see that max features 2 and estimators 3, then this was the result. If this is the, then this was the result, and so on. Okay, so this is what it has tried. So it has tried with, let me go back a bit. So here, 3, 10, 30. So 3, 2, 3, 4, 3, 6, 3, 8, 10, 20, 10. So it basically tried all possible combinations, right? And compared the result of the result of random forest regression. Okay, what is the root mean square error as of now? So the one with the least root mean square value is the one that got selected. Okay, that was the best set of arguments. All right, does it make sense to you, Vinta? Okay, so first we tried all other algorithms. So first we compared various algorithms. Once we finalized that the the random forest is doing good, so after that we further tweaked the parameters to parameters as in hyperparameters. What are hyperparameters? The parameters that you pass to the algorithm. Okay, whenever you're calling the regressor, the various arguments that you're passing to it. So, okay. Question from Kamal, but maybe fine-tuning the hyperparameters or other algorithm could have given the better performance. Maybe, but since we did k-fold on most of the algorithms, we could have got some kind of better indicator. And other thing is random forest gave drastically a huge difference, Okay, that's it. So honestly, the k-fold, the the k-fold, the comparison of various folds is a better judge than tweaking the hyperparameters. And we'll study further that a chance of tweaking the hyperparameter could be that we might end up we might end up kind of tweaking our algorithm, tweaking our model such that it fits this data well. Okay, that's why. So yes, you have it's a good point that maybe tweaking the hyperparameters of other could have given the good results. But since there was a humongous difference between the random forest and the others, therefore the chances of that happening is quite low. The chances of other algorithm performing better is quite low. Okay, uh, all right. And also, even though we are learning how to optimize hyperparameters, we'll also discuss that tweaking hyperparameters could be a dangerous thing in many cases. Okay? Because you are basically, what we are doing is we were basically trying to um, fit the algorithm to the current data set somehow. Okay, and in the end it may not give very great results when we run it on the other set of data. Okay, all right, very good set of questions. Let me try answering those. um, we got results, but what is the key point to identify this is a random forest? So we had discussed last time, right? We compared all the three main regressor models, and we will learn more about regression as we go ahead. So we tried decision tree, we tried linear regression, and we tried random forest. Correct? Okay. A question from Bentao: what is the content in my Jupyter different than yours? Your script with comments. Okay. Is it different? Because all I've done is I've checked out from there and started tweaking during the session. Okay. All right. Let me go back to where we were. Okay. So remember that we had earlier, where were we? We were, hmm. So this is what we did, right? While we were training, we basically, okay, here, right? After cross-validation of all the methods, we figured out that random forest was performing better. Correct, Neerav? And and then your further question is, we got results, but what is the key point to identify this is the random forest algorithm? We got the results, but what is the key point to identify this is the random forest algorithm? Um, so I did not get your question. Noor's question is, what is the default value of hyperparameters? Can we know that? And how to know what values to use for hyperparameters? Okay, very good question, Noor. So the question is, even though we are using 3, 10, 30, how do we know that it is 3, or was it supposed to be 5,000? Right? We don't know that. correct? So this is where a bit of knowledge about these algorithms come into play. And as we discuss in more details the regression models, this point you will learn easily. Okay, so we'll talk about what does it mean by bootstrapping, what does it mean by number of estimators. We'll also learn about the max features. All right, and
Uh, Sorry to interrupt you, Sandeep.
yeah, yeah, go
Can
ahead.
we? Yeah. Uh, I got it that we have tried various model and we identified that random forest is our better uh, performing model.
Yes.
But when we use a grid search
Mm-hmm.
CV, right?
Mm-hmm.
Based on that, we got a parameter 8 and 30.
Right.
So how can we say that this is the best parameter? This is the best result for random forest. In grade search is algorithm for to check the all the models and based on the max features, and based on that we can say that random forest is the best model.
So we are here. Here we are comparing the parameters, right, using grid search. And earlier, by using the cross validation, by comparing the results from other algorithm, we compared the result, and then we said that okay, the random forest is doing far better than the others. Okay. Okay. Yeah. Let me rephrase. Let me try understanding your question. Could you rephrase the question? I'm somehow
Uh,
not. Yeah, I'm sorry.
yeah, yeah, it's quite bit,
Yeah,
we tried various model like linear regression and decision tree and random forest, right? And we got
that's right.
outputs,
That's
right?
right. That's right.
And based on that, again we have used grid search
Right.
for identify which one is the best model, right?
No, no, no. Which one is the best parameter for this model? Okay, so here we are saying we're only asking, we're only passing the forest regression. You see
Oh
that?
yeah, yeah.
Okay,
Sorry.
so
Yeah.
okay, sorry. All right, great, good questions. And all right, now, all right, a question from Noor. Here we use 2468 for max feature. Why not 357? That's right. That's right. So we will go into more details that why it is, why we kind of have hunch that an estimator is 31030, not 5010 or 5 million, right? And CV equals 5 here. What is CV equals 5? CV equals 5 means the number of folds, right? Number of folds, as we had discussed. So internally, what it is going to do is it's going to take this algorithm, call on this kind of permutation. Okay, first it'll try this set, then this set. In this set, it'll try all multiplication of this and this cross multiplication, as in first it'll try n estimator equals 3 with max feature say 2, then an estimator 10 with max features 2, and so on. All right, so basically it's a kind of brute force search, or instead of we trying manually, we are letting it do that. Now question is, um, we learn that there are better ways to first figuring out better estimators, and one way is to learn about algorithm, and other in sometimes you could also use the next technique of hyperparameter optimization that is called random search. Okay, in which you could try really different arguments and then see the which values are performing better than the others. Okay, I'll show you. So my parameter grade is basically an array of dictionaries. Okay, parameter grade is an array of dictionaries, right? And each dictionary contains the uh, list of name of the parameter, right? An array of possible values. Okay, the value, or generally we keep, the way we keep in the parameter grid is this parameter grid is an array. You can see the array, right? It's an array of dictionaries. There are 1 and 2 dictionaries, and that way. All right. And each the dictionary contains key, and the value is an array of values which are possible values. Okay, now moving ahead, so out of this grid search we found that max features are 8 and number of estimators are 30, right? Now we figured out that this is these are the results when we run it. Okay, where did it go? All right, so this is what it shows as a comparison. And now afterwards, this is where we were till the last session. Now, the next is that the grid search was fine, but as we saw that as number of parameter possibilities keep increasing, the combinations become really huge. Combination become really huge, as in the say we don't know, let's say we don't know much about these parameters, for example. So imagine that we had put 50 values here. In an estimators, we said 3,000, 3 million, and 330, and 3, right? Let's say those are the estimators. So it's similarly, we had put many values in this array and so on. And as one value increases, it multiplies, as in 3 into how many parameters? 4. So total 12 plus 1 into 2, that is 2 plus 12, that is 14 plus, sorry, this is 3 into 2, 6. 6 in and 12. So total 18 combinations are there. But if you just increase this by one value here, what will happen is the overall will become 4 into 4, that is 16 plus rest, right? So it's as we are adding even one value in this, that means the total number of permutations to try, the combinations to try will become really high, and therefore calling this one actually calls your regressor, your function on the on so many permutations. So this function is being called 12 times. If we just add few more, it might become like 100 times we're going to call this. And each 100 time, we are further breaking it down into 5 folds. Okay, 5 folds. So they'll become 500 times we are calling the same algorithm on the data set. And then since the data is generally huge, and the algorithms are generally internally also, they are kind of trying to fit a curve or trying to fit a model, so they're permuting and trying to optimize. So algorithm itself are very heavy most of the time. So on the top one, the algorithms are generally very heavy. On the top of it we have folds, and on the top of it we have the grid search. It becomes really time consuming process, right? It becomes really time consuming process, and that therefore grid search may be a wise idea, but may not be more efficient, right? So to tune hyperparameters, we also use something called random search CV. So instead of instead of trying all possible combinations of hyperparameters, what we do is we basically pick the hyperparameters randomly on every iteration and try only few of those. Okay, so we try only few of those. So let me just show you an example. So like, for example, here we are saying random search CV, and say here number of estimators, we say we did not know the value. So we said generate some random integers between 1 to 200. Okay, so Okay, let me show you the value of this. How does it look? Okay, let me just take it here. Okay, so it should. All right. So is the way you look at it is okay. So all right. So what does I'm just trying to see what does this one return? So it returns something like okay. So here we are generating a random int. It's essentially an array of value low and high. That's what it is. A different array, different object. And that's what we are trying to see. Okay, let me just show you, give you the exact object. What does it mean by the RV frozen? Yeah. So basically it generates all possible values here. All right, this is a better way to do it. We could actually use this one as well. Okay, so essentially the random int generates this kind of value, but this is a bit different. No, the SciPy is okay. Let me put it again. So essentially what we are trying here right now is we are basically generating all the values from 1 till 200. Okay. Similarly, number of max features we are generating from 1 to 8. Okay. So and so on. So basically these are the as we talked about earlier that how do we know the values? So instead of we putting smaller values, we are just saying that pick any of these values. Okay. And then we are using the randomized search to pick few of these randomly, few of these out of it randomly, and then comparing them, and figuring out which hyperparameter is better. Okay. So that's what we are trying to do here. So this, so here we are calling randomized search, giving the algorithm name, and then we are saying the parameter distribution equals this, number of iterations. So here the important part is that we are specifying the total number of iterations. Okay, so this is something that we are freezing upon. So on every iteration, it'll pick a random value of this, and try it, and then see which one is performing better. Okay, and CV, we know that it is a number of fold. Where did it go? Yeah, so it's a number of folds, and then this is scoring, as in on what basis we are saying that one algorithm is better than the other. So we are using negative of mean squared error, right? Because we want to minimize the overall error, right? And then the random state, as we talked about earlier, the random state we are passing. Okay, so a question from Gopinath is, so that's 10 iteration per fold. You can say yes. You can say for each iteration, 5 folds. Okay, that's a better way to put it. So for mm in each iteration, what we are doing is we are basically going to call this algorithm 10 times, and every time we call this algorithm, the way we call it is we basically execute it on 5 folds. Okay, so we are calling this algorithm how many times internally? 50 times. Okay, all right. So we here we got some kind of let me run all the cells, run all above. Okay, that will basically run everything till here. So it's running right now. Okay, so question from Noor is, so we can say that it's a second option for fine-tuning the model? Yes. It's basically a little optimization on the grid search. Little optimization on the grid search. That instead of trying all possibilities, we are just picking random parameters and then trying it out. Okay, it is still running. Let it run. Question from Gopi is that did you get a chance to put the diagram from the last session? I had put it in this presentation itself. And what we're going to do is, since we are sharing the presentation live with you, so most of the diagram I'm going to put it in this presentation itself. So this is the diagram that we talked about, right? I think that will be better. Okay. Where were we? All right. So this is the random search model, and this one would have, yeah, it is running right now. So it's basically trying all 50 combinations, and so it might take a bit of time. All right. So all right. So the other way of getting better results is using the ensemble methods. Okay, and let it to finish by the time we can discuss it. So ensemble methods is we combine the best performing models. Instead of just picking one of the models, we combine them. And ensemble methods are more popular in case of, say, doing the natural language processing, and even in certain cases, the classifications. So the ensembling is basically, instead of just picking one and making them compete, and instead of just picking one winner, we pick up the best performing models, and then we group them either sequentially or in parallel, and and then we generally we ensemble them in a sequence, and we utilized the capability of individual algorithm in order to get the best results. Okay. Okay. Now, so all right, it is still running. Okay. All right. So the other part is that okay, good questions. Good question. The question is, what does combining models means? Okay, combining models means, let's say we are trying visual detection of images, right? So one particular image is working great on the letters. Other is working, one particular algorithm works great with the identifying letters. Other one is working great on, on say, the faces of people. And third one is working great on identifying objects. So we use all the three algorithms in order to get the best results. Okay, so that's called ensembling. Similarly, when we are doing text processing or text processing, we we basically want to identify certain patterns in the text, say a grammar and an emotion or some other thing. So we can ensemble multiple algorithms together instead of just using one. Okay, so so internally random forest is also basically the ensembling of the individual decision trees. Okay, all right. So a question from Kamal is, how can we use three algorithms to predict we finally choose one, right? Yes. So ensembling is a problem that we will actually, there's a full chapter on ensembling. And what we do in the ensembling is we identify whether a particular problem can be solved by ensembling or not. Not every problem can be solved with ensembling, right? Because in many cases, we really can't put the algorithms in the sequence. But in some cases, we can actually use multiple algorithms in a sequence. Okay. Um, in this case, we can't really ensemble the linear regression with the random forest or some other. Okay. But in the other cases that we'll discuss in future, the random forest would come in. Sorry, the ensembling would play a bigger role. Okay, so internally, the random forest is also trying to do some kind of ensembling, and yeah. So we'll talk about these later. All right. So a question from Gopi, what is the negative mean squared error in randomized search? Is it same as mean squared error? Yes, it's mean squared error with minus sign before it. That's all. All right. All right, let me see if we got some results. Yeah, we got some results. So it seems that the best parameters, right, are as per this are these. Max features is 3, number of estimators is 180. So that was based on random search. That's right, Tanmay. Okay, So, all right. Now, let's analyze the best models and their errors. Let's see the importance of each score of each attribute. So, in our model, in our model, there are many attributes, right? There are many attributes. We had rooms per household, population per household, bedroom per room, and so on, right? Now, once we have reached to a conclusion that we have figured out that this is the model that's working fine, and okay, so so we want to find out which of these parameters are the best, right? Are basically impacting our output the most. So we want to find out the feature importance. So there is something called best estimator, right? Using best estimator gives us what? Best estimator gives us this kind of, where did we go? Let me go up. Yeah. So best estimator gives us which in the grid search or search, random search here. In both the cases, it gives us the best estimator, and the best estimator is essentially the name of the algorithm along with its parameters. Name of the algorithms along with its parameters. That's what is the best estimator means. Now, along with that, it also gives us something called the feature importances, right? So if we go down a bit here, okay. So the feature importances is after the grid search, it the it has also given us the importance of various features. Okay, so the importance of the features means the which feature is impacting our output the most, which feature is impacting the the output most. Okay, so this is useful when we are trying to understand further about our data, right? So let's here this is an array of various features, right? Various what do you call the feature importances. The first feature has got this much importance, second one has got this much, but it doesn't make much sense. So let's put the names on it. Let's put the names on it. So what we are doing here is we're creating this, we're getting all the attributes from our pipeline here and extracting the names of all the attributes and then combining that with the extra attributes and one hot attributes. That's what we had passed in the final one, right? Si- And since the NumPy array did not have the name of the columns, therefore, we are assembling the name of the columns again from the beginning, right? So once we are done with that, we'll zip it. What does zip do? Zip basically brings the two elements of the parallel elements from the two arrays together. Okay, that's what zip do, and then we are printing that. So the result that we get is this. It shows that okay, so this I'll show you this one, right? So median income is the most important one. Median income, median income of the median income of that particular block is the most important parameter. Then one particular category called inland. Inland is the another very important feature of the data, that if our house is having the attribute called inland, then it's impacting our output really well. Okay, if this is on or off, that is that's changing the house value quite much. Okay, so basically the inland is having a good impact on the output. Then population per household is the third best parameter, while longitude, latitude, and onwards have very low importance. Okay, so question is, what is inland and what are these? Basically, remember what we had done? We had converted our one attribute called proximity into multiple categories, right? Into multiple columns, into something called one hot encoding, right? These are those. Okay. So this is the value of inland is true or false, 0 or 1. Similarly, the value of these other category variables, these other category values is true or false, right? So not as small as the best, but the biggest the best. Okay. And this is the smallest one. It has 10 to the power minus 5 on it. Okay. All right. Good. Good that you noticed. And uh, any other question at this point? So basically we got the feature importances. This is part where we analyze our algorithm and the results. So so while we do the grid search, it also gives us the feature importances. Okay, so you can see that I think we can also ignore the longitude. These three parameters are These three parameters are the most important parameters. The median income, whether it's on the land or not, then the population per household. These are the three good indicators. Yes. So higher the factor, higher the significance. All right. Is that right, Ross? Gigi? Great. Great. All right. I'm just checking if you are around or not. Okay. I see. Okay. Okay, so if you combine some of the features, we might get better direction. Yes, yes. So, all right, all right. So, yeah, Dharma has a question. It's a very good point. If we try more permutations of combinations of these parameters, we might get a better direction. We may or we may not. We may or may not. And we will learn in future that how we can further figure out more combinations on the various parameters. All right. The way we had computed population per the rooms, what was that? The the total number of bedrooms per rooms, correct? So those kind of things. All right. Now the good part about the what do you call coming back here? Yeah, the good part about feature importance is that if there is a derived feature out of the basic features, okay, that gets a lesser importance. Okay, so basically inside your features, so there were two things we talked about, correct? One is called correlation, right? Other is feature importances. Correlation had a similar connotation, similar as the feature importance, right? I was hoping that somebody would ask that question. Um, all right, so okay, so all right, so feature importance is feature importances are different from the correlation. How many of you remember that we talked about correlation? CORR method in that NumPy. And what did it do? Nobody remembers? Yes, yes. So, so the correlation method in your data set tells you that which feature in the data is correlated with which other feature, how in how way, in what way, whether increasing a value has an impact or not in the output or not, right? So the feature importances are very similar to the correlation, just that in case of feature importance, what it figures out is if there is another feature which is dependent on one feature, it basically figures out that relationship between the parameters. Okay, that relationship. Okay, so feature importance is the better indicator than the correlation. Okay, it is the better indicator than the correlation. So this is kind of after using algorithm and scanning through all the data, trying all hyperparameter optimizations, it figures out that these are the features which are these are the features which are more important, and these are the features which are less important. Okay, so even if our data was missing these columns, still we'll get good enough results. Okay. So further what we can do is we can just pick if we want to make our learning faster. Let's say we are trying to do an online learning and we want it really faster. We can remove the other features. Okay, the accuracy might drop down. Accuracy will drop down, but it won't be that inaccurate. It'll be okay. All right. A question from Ross, is that a generic statement or specific to this problem? So it is basically generic statement saying that the feature importances are better indicator than the correlation in general, right? So if you remember the bedrooms per room that we had calculated, so even though this was giving a very good correlation with our data, but it is derived attributes depending on the other attributes internally. Okay, so the other attributes have a better impact on the output. Okay, so a question from Kamal, how does feature extraction decide which feature is more important? Is it about the delta change? And a good question, is basically while going through the algorithm, while trying all, uh, internally the algorithm is trying trying to fit the, I mean, trying to fit the model on each record. At that point of time, it is observing the impact of the value of a feature. Okay, so that's how it's computing that which feature is more important. Okay, so okay, all right. So let me rephrase what I was saying. So while the grade search was going through, right, it was basically internally calling the algorithm on various records in the data, correct? At that point of time, it has been observing that that which feature which feature change is impacting the results more. So as part of the scan, that is happening, right? And most of the algorithms in scikit-learn provide the feature importances. All right. Let me go through a few more questions. So here we are saying that house pricing is dependent on median income, then category, then population per household. Yes. So the most important feature is the median income. Okay. So house pricing, this feature is impacting the house pricing most because the value is highest here. Then inland is also impacting whether inland is yes or no, that is impacting the results more. And the population per household is also impacting, but little lesser than the inland. Okay, and then the longitude. Okay, all right. I hope that answers your question, Noor. Question from Tanmay. Shouldn't we drop the derived attribute? We don't need to drop the derived attribute. Okay. So, yeah, we were basically, there is no, need to drop the derived attribute as such. The other question from Ross is, can you give an example when a derived feature input is better than given feature data? Okay, all right. Okay, so that'll be a little harder at this point. Okay, let me rephrase the question. Can you give an example of when a derived feature input is better than given feature data? Okay. So sometimes the nonlinear relationships between the features, let's say our result is some way having a inverse relationship with some of the features. So maybe if it's a complex relationship between the output and the input variables, in those cases, and we know that part for sure, in those cases, we might improve the result by combining these variables, the features, more creatively. Okay, so in those cases, that result might improve. Okay, result might improve, and the feature importance could be better in that case. All right, but that's really rare. That's really rare. And the overall idea is that the the algorithm that we are using, that should generally we choose the various algorithms such that we don't need to do a creative combination of various parameters. Okay, so let that be figured out by the algorithm, and if we know, if we knew about a certain relationships between the variables or the features, then we should do that. If we don't know about that relationships between the features, then we can't really create a derived one attribute. And say, for example, here, the the bedroom per room is something that we got a hunch. We tried that, right? And it did give us a very good result earlier. And it's actually still a good feature to have. It's better than the other ones, the island ones, though it looked These near ocean looked very good from the visual perspective in the beginning, and so bedroom per room is still a very good feature, but it's not that important as compared to the other ones. Now coming back to the question is that can there be a case where derived feature is more important than any of the basic features, right? When we are computing. So there could be a case whereby there's a complex relationship between the features, say 1 by household square plus 1 by total rooms square, that really can't fit into say linear regression or any other models. In those cases, the chances of that particular feature becoming more important is very high. Okay, did I make sense, Ross? Okay, a question from Gopinath. Would you then simplify the model before evaluating with the test by dropping the not really required. Not really required. So the less important features we can drop at a later point of time. In case, see, these features are less important, but they are still contributing to it, right? They're still contributing to it. And say, for example, latitude and longitude, they are 0.07, okay? They're still significant. So the accuracy of our predictions will drop if we remove these features. Okay, the accuracy would go down slightly. Okay, and all right. A question from Dhanma. We dropped something in our calculation a few classes back. Don't remember what. What did we drop in our class? Okay, I think we dropped that variable in which we created a new category variable for for the for picking up the records from every bucket equally, right? That column we had dropped. That column we had dropped, I think, because that was no longer required. All right. Okay. A question from Node, did anyone get a result from random CV? I got an error. So I did get a result from the random CV here. Okay, if you go up, I did get results, right? Okay. Try that, probably run all the cells above and then run it. Okay. Yes. Yes. When we created the stratas, and then that time we had dropped the column. Now, a question from Kamal. What is the purpose of feature instances importance? Good question. Let me try to give you an example. So what we observed just now is that whenever we are running an algorithm, whenever we are training it, it's taking too much of time, right? So let's say we want to run this in a real-time environment, as in the data is coming in and data is huge, and we would like to run it really fast, right? In those cases, we may want to drop some of the features so that the overall algorithm becomes faster. So instead of generating the model based on all of the features, we will basically keep the most important features to kind of improve the time, as in improve the time consumed by the algorithm execution. So specifically while running an algorithm in the real-time environment or training in the real-time environment, we might let go of some of the accuracy and might just want to consider the four most important features. All right. The other thing is, when we are dropping the features, we also are minimizing the use of the memory. Okay, so for the performance reasons in terms of the memory and the CPU, we might prefer to drop some of the attributes. All right, good question. A question from Tanmay, is it pushed to Git now? Yeah. So I think everything is should be in the Git. A question from Balaji, is it possible that the features might change from time to time? Okay. I think I got your question, Balaji. Question is it possible that the features might change, as in the feature importances might change from time to time? That's a very good question. That's what we am coming to in a while. Okay. All right. So a question from Minto, could you post your Jupyter scripts link since mine is different with yours? I'll actually check out and make mine similar to yours. Okay, I will overwrite what I have written and that'll be better. Okay. And anyway, I think whatever is there in the repository, that's the correct one. Okay, that's the correct one. So this should be correct. All right, this is correct one because I will also check out from here. Okay, this is the correct one. Yeah. Yeah. So this is where we are, right? All right. So this is the correct one. So please take it from there. Don't worry. And I'm also going to probably check out that one only and ignore my changes. Okay. All right. So there are a few more things that we would like to talk about. So we are kind of towards the end of this project, this end-to-end project. Now is the time, once we have fine-tuned our model, we have done all kinds of things. We did um, we did k-fold search, we compared all algorithms, we did the hyperparameter tuning, then we did the what do you call randomized search and so on. So we compared the algorithm, figured out which algorithm is best, and we ran that algorithm on the subset of our input data, and then and we are in that last point where we want to run it on the real test data. Okay, real test data. Before that, there is a question from Binta. What are category pipeline and named steps respectively? You remember we created a pipeline, and that pipeline in the named steps contains all the information about various steps. So from that, you can we have extracted the categories, the names of the columns. Okay, there was no easy way to just get those columns, so we had to create that list again. Okay, so we got category hot one attributes, we got extra attributes, we got numeric attributes. So that's what it is. So since the NumPy array does not have column names, so that's why we had to recreate it. Okay, so this was our pipeline. There was two pipelines, right? One was numeric pipeline and other was category pipeline. And out of the category pipeline where we did the data cleaning, we had something called category encoder. In that category encoder, we got the one hot attributes, right? So that's what we did. All right, good question, good question. Now, after tweaking the model for a while, when we are confident about the model, then the time is to evaluate the model on the test set. So we get the final model. using, so we are ignoring the random search here. We are going with grid search. Okay, we could actually pick up the random search. There's no not much of a big deal. Okay, and the final model we are picking either from grid search or randomized grid search, randomized search with the member variable called best estimator. And once that's done, so now we are doing the same thing with the test data. Remember, we had split the test data into two. We have split our actual data into two parts, and test data we have not yet touched. Okay, test data we have not yet touched. So from the test data, our target column we are keeping it in the Y, and rest of the columns we are keeping in X. Okay, so after our stratified, we had generated the stratified test set earlier long back. We are now breaking it into two parts, X and Y. These are the features, and this is the target variable or labels we call it. Then, using the same pipeline with which we had processed the other data, we are processing the test as well as right, we'll be doing the similar processing for Y as well. Okay. So I think Y, yeah, I think Y is not needed to be processed. Okay. And then what we are doing, this is the important part. So here we are saying final model, whatever has come out of the grid search, we are calling that final model, we are calling predict function on that final model with this prepared data. After our pipeline, this is what we get. Okay. And we get the final predictions. Now we want to find out how well these final predictions, how well these final predictions are doing with respect to our label data. So we are comparing final predictions with y-test using mean squared value. Okay, this is basically the mean square, and then root mean square we'll have to do the square root. Okay, so our overall root mean square of error is around 47,000. This is the error. This is the error, overall error in our test data. So when we did the prediction, these were the predictions. We subtracted every record of predictions from the actual and then did the square and summed it up. And afterwards, we are doing the square root of this. So basically, this is what shows the accuracy of our model. This is the overall error. This is the overall error in our model, which is good enough for now. All right. Okay, so let me go back here. All right. So x is equals 1 means that we want to drop that column, not the row. Okay. Yeah. Thank you, Gigi. And good question. Now, moving ahead. Now, what we see here is, let me run this. Okay, go up. This is done. Now, is something going on here? Oh, this is not the one. Let me go down here. All right. So again, let's run it. So we've dropped this, we have transformed the test data, we're predicting the text, predicting the transform data, we're predicting on the top of transform data, and these are our final predictions. And then we are subtracting this from the actual predictions and squaring it and summing it up, and then this is our final value. Okay, so this is the error. All right, so what we have finally trained and tested our first model. All right. Okay. So did everybody get this result? Did anybody run it? Okay. So this is the error that we got from the testing, from the test data. Let me go back somewhere, right? I think this is very close to. I'm just trying to see that in the cross validation, the kind of error we got this error, right? 49 something. Yeah. All right. So let me go back where we were doing it. Okay, so actually we got a bit better here. After fine-tuning the parameter, we got the accuracy because before the before the before the hyperparameter optimization, our results were 52,000, right? So hyperparameter optimization did solve some of the problems. Okay, after the I think we did here, right? The best results, where did we do? Okay, where is the grid search? Did we override the grid search? Yeah, yeah. Okay, in the grid search, I think it was this, correct? So let me go back. So our this was from the grid search. So it's not bad. It's actually better on the final test data. So we did not overfit. We did not overfit, and we did it did a good job of finding the best value. All right. So congratulations, we have trained and tested our first model. And okay, so question from Binta is, I wonder what we can do with the final model as a buyer. So what we can do is we can prepare the whatever wherever we are looking for the house, we prepare the X test prepare here. We prepare the X test and then do the predictions. That's all. And we'll get the results. Okay, that's what we'll have to do. We did not do ensembling. So if I'm a buyer, all I will do is I will basically prepare my array in the form of X test and then run it through the transformer, whatever transformer we had, and basically then pass it through the predict. So these are the two lines of code I'll have to do as a buyer. So we'll prepare one row and that's all. Okay, so a question from Noor, how do we know what is the value of root mean square error? So root mean square basically has to be as small as possible, okay? And therefore, therefore, the 0 is probably the best value. Okay, so here that's why we are comparing multiple algorithms to get the best value. We we are trying to figure out that how we can achieve this at 0. Okay. Okay. All right. So yes, let's now there are a few more things. It doesn't end here. Thank you, Gopinath. Okay, there are a few more things that we would like to discuss. This model is not perfect enough, correct? This model is not perfect enough because still we have a decent amount of error, but this is good enough. Okay, we will also learn and build better models as we progress in the course. And now there was a point that some of you raised, that why are we aren't we kind of um, using hyperparameters too much? So hyperparameters sometimes, if you do a lot of hyperparameters tuning, then the performance of the model can be worse than the performance measured in the cross-validation. Okay, this happens because the model is fine-tuned to perform well on the validation data and perform badly on unknown data sets. Okay, so we are kind of trying to see that if we are lucky, right? At many point of time when we are doing too much of hyperparameters, we're just trying to figure out if we are lucky with the current data set, right? And that's one of the reasons why we had separated our test data from the main data, so that we do not hypertrain uh, uh, our parameters in order to just fit our model to the current data set. Okay, and will not perform. In that case, we have to ensure that our model should perform well on the unknown data set. Remember that when we gave the entire data set to random forest, it basically gave us 0 error. I think, yeah, I think that happened, right? In decision tree, probably it gave us 0 error. Basically, it kind of overfit entire thing. Okay, so that's why we have to be cautious with respect to hyperparameters. And because our model must generalize to unknown data, something that we do not know, so that we can trust it, so that this algorithm can be trusted. Now, once that's done, we can present our solution, what we have learned, what worked and what did not, what assumption we made, what are the model's limitations, and a very important part that we must document everything. Okay, and yeah, and we need to create nice presentations with clear visualization. And this is the part that I always miss out, that while presenting our model, that instead of because when we are presenting a data science solution or a machine learning solution, we need to prepare a proper presentation. Okay, because a lot of data science is about communicating the results to the various stakeholders, and the results should be convincing enough for the end buyer, right? Otherwise, if we are not presenting our solution neatly to the end buyer, they may never trust this solution. Okay. All right. A question from Tanmay is that what do we deploy in production? Bunch of Python file also in prod. If the RMS is too large, what should be our action? When should we consider retiring the model and restart? Very good questions, Tanmay. I think those are the things that we will answer now. Okay, those are exactly the questions that we need to answer now. Those are very good questions. A question from Noor. I'm sorry, but I did not understand the RMSE thing. Like, how do we know that 47,000 is a good value? Okay, so let's see the root. Let me go back. So okay, let me try to answer that. So 47,000 error was there, right? So it was the summation of all of the values. And if you take a look at it, it is essentially the overall error. So which means that we generally take a look at this value and see what percentage of the total value it is. And in this case, the overall percentage is not very high, but it is not also very low, correct? The important part to understand here is that this is the best value we could get out of the predominant algorithms. Okay, this is the best value that we got out of predominant values. Yeah, so it's not really great, but it is good enough in the sense that if you take this value and compare it with the, compare it with the actual value, then you will see. Okay. A question from Minta, is there a summary, structure, architecture, flowchart for this long script for our understanding memory learning? Good question. Good question. I think I'll prepare a good chart for this. That's what I was actually doing just now. Okay. So I'll actually prepare a chart in which whatever we learned, we can present it better. Okay. Uh, so that's all. All right. I'll do that. Good point, Vinta. A question from Ross. The error was still pretty high relative to the price of home. Yeah, that's right, Ross. Um, it will basically summation of all, and if we kind of average it out, then no, it will be the root mean square error. That means it's already meaned, and therefore it is how much is how far is it from the actual value. Okay, so you can take a look at it. So this is the house median value, right? And our and what did we get? We got this, right? Root mean square value, which is how much of this? Okay, so you can see that the error is around 10%. The overall error is around 10% in some cases. Okay. A question from Gizi is that error is dependent on the data. No, error is dependent on the data as well. Yes. So if the data is erroneous, so we no matter which algorithm we try, there could be this much of error. The error could be insufficiency of data. The error could be insufficiency of because of insufficiency of the features. The error could be because of our algorithm not performing great. There could be better algorithms out there who could do the better job. Okay, but it's mostly because of incorrect data or insufficient data. Okay. Okay, a question from Bintao. How many packages, libraries, modules are used in the session? So we have generally used NumPy, Pandas, and from time to time we used SciPy. Okay, and for square root we used math and matplotlib. Good, thank you, Giri. All right, so basically those were the main libraries that have been used, and scikit-learn. So let me put it. Okay, pandas, numpy, scipy. Scipy from time to time for individual functions like picking the random integers, and numpy, scipy, scikit-learn, and matplotlib. Okay, so these are the libraries used. Okay, so what I'll do is I'll basically prepare kind of this flow diagram of what we have covered, and I think that will be better. Okay, the important part in this is there was this sheet that we talked about in which there were a list of things that we generally the approach to machine learning problem. That's something that we had discussed earlier. All right, good. There are a few more questions. A question from Tanmay: how do we take care of special situations like recession or localized natural calamity, etc.? Very good questions. Let me just get to that. Okay. Question from Gopinath: how do we know based on the difference between training and test error as to whether the model should be refined further? How do we know based on between how do we know that based on the difference between training and test error as to whether the model need to be refined further? Is there a threshold? There is not a threshold as such, but if your model is performing really well on your test on your training data and is performing really bad on the test data is on the test data, the if that is the case, then probably you will have to reevaluate one, the way you have split your test data. Second, did you overfit the model, or did you do the cross validation or not? And and while creating the data set, did you do stratified or not? So those kind of things you have to take into account. All right. And a question from Gopinath: is there a threshold? There is not a threshold, and 10% is yeah, 10% is what it's basically saying. It is as good as it gets. All right. Okay. So all right. Mm, One is this flowchart we talked about. Remember, Vinta? It is on 396 slide. Okay. All right. A question from Gopinath: my PDF has only 298 slides. Mm-hmm. Let me just show you that. Okay. Um, all right. We have tried to embed the Google slides. So instead of PDF, because PDF, the updating was becoming a problem. So instead of that we have basically embedded the Google slide itself into the presentation. You can use that. If it is not, we will do that probably in the middle of the session or maybe by the end of the session. Okay. All right. So yes, that way it'll become easier because it was becoming a big issue that we were whatever we change during the session, we need to update in the PDF. Okay. Okay. Uh, Good questions. Good question from Noor. Let me answer these questions one at a time. Uh, we accepted this as good value based on what? One, it's not, it's basically 10% kind of error, which is okay-ish in most of the algorithm cases. And why did we stop here? Why did we stop here is because, right? So why did we stop here is because we wanted to give you a good overview picture. As we go ahead in the other sessions, we will learn the more about details about more algorithms. We will learn about deep learning. We'll learn about neural networks and see if we can use those in order to improve the accuracy of this one. Okay, and we will the random forest is generally known to do good results. That's why we kind of stopped here. Instead of going further, comparing further, we wanted to close the end-to-end loop that should give you an overview picture. All right, that is the sole idea. And there are, yes, there are more algorithms. We will go into more details as we go ahead. And when do we have to take a decision to create our own algorithm? Okay, so that is something, the way we generally do is we tweak the existing algorithms in order to improve. If we realize that something is not doing good, in those cases, we generally modify, right? We generally, we not, we don't generally modify, we modify only in the cases that we know for sure that a particular algorithm has got a bug and we have got a better idea than this. And that takes quite a much of time, and it takes a good amount of time to prove the correctness of the performance and the correctness of new algorithm. All right. So somebody was trying to unmute. You can go ahead. Who was it? Okay. All right. Now, next is when do we have to take a decision to, okay, is this RMS value accepted value to be directed in the business? So that's a good question. That's a good question. So generally what you do is, that's why we went in the beginning, right? That's why we went to the experts, those who were predicting, and their error was around 15%. So our error is around 10%. So we have improved by 5% margin. That's a very good value to have. Okay, that's a very good value, and a, and we are no longer dependent on human error. All right, so that means it is the accepted value. Okay, had we not, and all the time, as a thumb rule, whenever we are optimizing something, doing performance, you always start with an existing benchmark. That this is the kind of error you get right now, and we will improve upon that. Okay, had this had this error been worse than human intervention or human predictions, then there was no pressing business case of deploying the algorithm. Okay, so that's one way. Did I answer your question, Noor? If we have more than one categorical columns, do we need to factorize every? Yeah.
Hello,
Yes, Noor, go ahead, please.
can you hear me?
Yes, I can hear you.
Uh, Sandeep, I got this.
Mhm.
Actually, as you mentioned that the business said 15% was the error, right?
All right,
And now we got the 10%. Okay, so it's better value than what we originally had.
that's right.
But, but this 10%, but what I'm trying to understand is this 10% is a difference between
Mhm.
the error from test data and the error from training data, right?
This 10% is, I mean, I'll give you a quick example. And here, this 10% is on maybe testing data. Yeah. So this error, right? 47.766 was mean error on the of
Uh,
the result, right? So I just picked up one
test.
value. Yeah. Yeah. So this was our test data only. Yeah.
Yeah, this 47K was from test data, and
Yeah.
this 45,000 from the training data, right?
Some data.
So it's
Okay.
from one of the record, you mean to say?
Yeah, I just picked one just to indicate the percentage. That's all.
Okay, got it.
Okay. Okay.
Okay, that's what
Okay.
I wanted to understand.
Yeah. Yeah.
Thanks a lot.
Okay. No worries. No worries. I just wanted to give you a feeler that how much percentage it is. Okay. Ideally, we would actually like to, when we talk to the businesses, we'll ask about their historical results. As a systematic process, what you should do in the business cases is that you sit with them, make a list of the last errors that they did, right, and make a note of their mean error. Okay, and then compare the mean error with the results here. Okay. So percentages are just good for our own references, but mean error is far better because mean error is overall, while percentages could be on one value against another. Okay, so mean error is something far more stable, better way of judging the performance, and that's something that we should follow. Okay. Um, okay. Great. Great. All right. So. Oh, it's already 8:48. So let's take a break and then we'll launch the system. All right. Okay, so all right, so let me write it here. Break for 10 minutes. Right. So I'm back. Should we start now? Hi, everybody. So I'm back. Should we start now? Great, great. So we have trained our model. Now, basically, is the time to launch it. Okay. So launching is basically first is we need to prepare the solution for production and plugging in the production input data sources. Okay. And again, a lot of challenges do come at this point. Okay. A lot of challenges do come at the point. Trust me, as I mean, for example, I'll tell you that one of the models that we prepared in Mobi, we basically were we were assuming that we will be given 4 GB space, 4 GB RAM on the individual node inside our Hadoop cluster. So we were basically running a distributed what do you call recommender engine. And there, what was happening is when we were trying to plug in our model into production, one of our data pipelines in which we were transforming data was consuming more than 4 GB of RAM. Okay, and they had this strict guidelines saying that we cannot go beyond we cannot use more than more than more than 200 megabytes of the RAM. Okay, so this is a very interesting and hard part in the industry, and probably this is the most ignored part by most of the data scientists. All right, so for a couple of reasons that one, the access to the production environment may not be available to you, so you will have to document the entire process to how to plug in your model in the production. Second, the environment would be different, so all the dependencies that are required for your model should be available, like scikit-learn has to be available. Similarly, the input data sources, the specification of all should be very, very clear. So those parts are something really, really come with come with practice in the software engineering. And and this is the part which I saw in past as a point where most of us actually gave up. Okay, so plugging the basically, let's say we are happy and we are launching our system, right? So going back to the point, so what do we need for our solution to run? Our solution, what we need to run these uh, three commands. Let me just go back to the example. I think that'll be better. So what do we need in our example in the production? We need these few things. We need to run basically whatever is the data, we'll have to run this function, correct? Transform the pipeline, transform the pipeline and predict, which means the pipeline, the code for the pipeline has to be there, right? And we need to also prepare this stratified testing. So we will have to create a very clean function documenting the expectations of input and expectations of the output here, and create basically a function out of it that given these values, we should be able to prepare, we should be able to give the results. Okay, so not only from the numpy array, maybe as arguments also, if somebody is providing all the parameters as argument, we should be able to do that. Okay, so we basically create a separate program which has a clear expectations of input and clear commitment to the output. And then we also inform that our dependencies of the project are going to be Python, scikit-learn, NumPy, and their various versions, and that we inform to the production team along with our project. All right. So the clarity on the requirement on the software side, data input side need to be communicated well. Also, while we are at it, we need to be clear about expectations, as in how much memory will our program need. So we might have to test while running the transform that before putting it in production, that how much memory are we consuming by using the ps command and top command in Unix, and there are a few more systems, and then and once we are okay, and we know the production environment that this much memory is allowed, only then and we are fitting in that, only then we push it to production. Otherwise, we try to kind of bring down the memory consumed at various places. What if the program was supposed to run on a very thin device which has hardly few hundred megabytes? So in those cases, we might have to do kind of feature trimming. We might have to remove some of the features and prepare the model and so on. Okay, so this is one way. So here, all I'm talking about is deploying the model. But at a lot of time, what we also do is we keep on monitoring the performance of this and keep on building the model again and again. In some cases, we do that. But uh, in most of the data science projects or machine learning projects, what happens is you do the training on different machines, and do you deploy on different machines. For example, in case of Amazon, the the recommendations, for example, that's something that we all see. Those recommendations are prepared on different set of machines. Okay, and once that recommendations are prepared, that results are pushed to the production. Okay, and in case of other systems where we are, let's say our this one itself. Imagine that we are having a website. We are providing this as a software as a service to people. People would come and input select the area where they are trying to buy, and key in all the values that they are looking for. They select particularly area. They know that if they are buying for 2 BHK, 3 BHK, or they are buying um, this many square feet, and so on. And they basically key in those values, and then your model will run there. Correct. So mostly what happens is you generally run you generally train your model on different set of machines and run on the when you predict on the different set of machines. Okay, so you should have a clear expectation of both the machines. All right, and this is something that is not covered in the presentation, but this is something based on my personal experience, because this gets ignored very often. Okay, and because when you're not able to launch the system, let's say you plug it into production and things are not as per your expectations, what happens is that you kind of give up at this point, that it's not my job. But it is the job of data scientist to get end to end done, take it to the production. All right. So yeah, and because if with the adversities of the production environment is something is something that we the adversities of the production environment is something that we um, that kind of guide us to change our way of thinking. So in our case, I'll give you a better example. In our case, the same case as in Mobi. So we were given 200 megabyte of memory while building the entire system of the pipeline where we were doing the data cleaning everything. We were assuming that we will be getting 4 gigabyte of memory on one of the machines. So while we pushed to the production, they pushed it back saying that we cannot launch your system because your system is consuming so much memory. So at this point of time, it was very prompting to say that it's not my job. It's very prompting for us to say that it is all politics. But the truth is that it's when our algorithm is consuming more memory than what fits in the production, right? So we might have to readdress say the data cleaning steps. We might have to readdress these steps and figure out why it's consuming so much of memory and other parts. So this is the part where the software engineering comes into place. So we really cannot ignore the software engineering, specifically in these kind of steps. All right. All right. So that was something. Yeah. So at this point of time, yes, we had ignored a lot of. This is something I have seen failing of like 4 to 5 data science projects, and for exactly the same reason, called for not plugging in not being able to put it in the production. Okay, there are many things, as in since the time the data format was given to you for training, you studied it, you spent like 2 months in building the model, but by the time you put it in the production, the input data sources have changed, right? input data sources have changed. And at this point, in case you had done manual tweaking of parameters, and if you don't have done, you have not done created the pipeline, the chances of you putting in production goes really low, because if the input data sources, if you did not prepare things like full pipeline and did not do the transformation, it won't be possible to put it in production. And this is something that Kaggle may not be able to teach, because because most of the things that we take for granted is that the data formats and production is something to no, not in our control. If we are just looking at problem solving perspective, but in the real scenarios in the industry, you will face this challenge. Okay, so at this point of time, expect that there would be delays, because there will be more parties involved. There will be more newer systems will be involved. And the only thing you can do at this point is to make your entire system to be as much automated as possible. Have a finer control over the libraries that you're going to use. For example, let's say in production, you realize that Python is not allowed. Python is not allowed. So what you would do is you will have to go back and prepare a pipeline in the language that they are allowing, or bundle Python with your own program. Okay, so those kind of challenges do occur. Those are data science challenges, and we need to be ready for that. All right. A question from Noor. In production, algo will only apply to new data, right? So less memory. That's correct. That's correct. But you have to be very clear about the memory and CPU expectations in production, right? Okay, and it's doubly challenging when we talk about, say, Amazon web page, right? Because the kind of real state you are expecting there, it has to be as per the expectation of the detail page, and so on. So you will see a lot of difference in the expectations, right? And again, if you guys are aware about the service models and other things, it makes it easier to put things in production, right? So in let's say in case of Amazon, the individual section of the website is rendered by different teams. Okay, so different teams are responsible for different sections of the website. So it becomes easier in case of Amazon to push things up, put more things on the website. But in case of my previous experience at the InMobi was that their ad serving engine was basically a separate team altogether. So injecting anything into ad serving was really impossible, because it wasn't based on service model. Because in case of ad serving, the performance expectation was really high. Okay, so it was kind of hard at that point. So you need to you need to be very clear about what production and where are you going to fit the model, right? That's why, if you remember that diagram in the beginning, we talked about there was this diagram in which we were saying that this is where our model fit. So understanding that point is very important. Knowing what environment it is, what versions of various softwares are available there, what is possible, is there a chance of upgrading the infra, what is the hardware needed, what's the memory, what's the expectation, how much, for how long can your program run, and all of these things have to be very clear to you, okay, wherever your model is going to sit, because that's going to dictate your engineering approach. Okay, now in the production, yes, sometimes it is we don't, most of the time in the production we don't train, but that's what we're going to talk, that where we need to keep on updating our model as well. Okay. In our case, mostly we have run the model at the frequency at which it can finish. So some of the algorithms used to finish in something like 3 days. So the training will go on for like 3 days. And in those cases, every 3 days, we would just keep rerunning the entire thing. Okay. And once that is done, we keep on pushing that model to the production. And in production, the results are computed really fast. Okay, so and it must consume lesser memory. But what happens is in the production, in the model expectation are different from what we have. So sometimes the memory keeps on going up. Okay, so even though in production we apply only on new data, and therefore there is expectation that it would be really fast in production, but sometimes it might go really slow as well. So know the worst case, best case scenarios. That's the only thing, only advice I can give at this point. And a question from Bintao: could you write a code to plot Y test against final predictions in the same graph? I would like to view the difference between them. Okay, Y test. Okay, we will do that. All right, sure, we'll do that. I'll just make a note of it. All right, good. A question from Noor: is there a documentation system or system which can predict resource usage for various algorithms? And if we provide data length in order to estimate cost of production rollout? Yes. So there are various performance test tools that provide you these mechanisms of computing time. And memory, I'll have to check. There should be something in the memory. In case of Java, we did have some tools earlier. I need to check if in case of Python, what are the tools to do the performance testing? Okay, performance with respect to the hardware. All right, great, great. So moving on. Okay, all right. So yes, let me just make a note to myself. Okay, so perf testing tools. Okay, let me see. All right, now, so once you launch, you need to monitor the system. Okay, monitor the system. When monitoring code to check models live performance at regular interval, we we need to keep an eye on we need to keep an eye on our model's live performance. Okay, whenever the performance drops beyond certain level, okay, or we need to trigger alerts. This is important to catch performance degradation as the models tend to rot. There are, as suggested by Tanmay, that there could be there could be all kinds of different changes in the climate and the various circumstances. The model could start misbehaving. Your predictions are suddenly going really high. The root mean error is going really high. So you need to keep an eye on this. And as soon as if if deploying a model, retraining the model is not something that you would like to do periodic, you must need to keep an eye on performance degradation of the algorithm as the models start rotting after a point of time. Okay, what does it mean? That we trained on something else. After a while, the data had changed, the trend had changed, and therefore the 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 overall performance will degrade, right? And okay, sometimes if you have a chance, then plug human evaluation pipeline into the system. Like in case of Gmail, they have put a report spam and other things. So sample the model's predictions and evaluate them from time to time. This this generally requires human analysis. These analysts may be field experts or maybe from a crowdsourcing platform such as Amazon Mechanical Turk as well as Crowdflower. Okay, basically, from time to time we need to plug human evaluation into the overall pipeline. Okay, so a question from Noor: what was the hyperparameter value which gave this result? Okay, I think that we have mentioned earlier the best case scenarios. Okay, all right, good. Thank you very much. Now moving ahead. Okay, so somebody was saying that what if the results are way off or results are not as per line? So you can actually plug in the human evaluation pipeline, have field experts or have the crowdsourcing platform. Or I mean, not everybody is as lucky as Gmail is, where they can provide a button and people could report things as spam and not spam. Using those, you can basically start using human intervention. You can start updating your algorithm. Now, from time to time, we need to evaluate the model's input data quality. Performance may degrade if the input quality is not good. For example, let's say after a point of time, sensors start sending random values. So suddenly, if the sensors or the input data that's coming in, it starts, it is not good. Then in that case, the sensors, in that case, the result of your algorithm could be really bad. So, and the monitoring is specifically important for those systems in which the training is happening in the real time. Okay, if training is happening on online in the online data, what would happen is that the data has become rot, as in the sensors are sending wrong data. There are all kinds of uh, errors, and eventually the model is kind of deteriorated completely. Okay, and that could happen very much if in case of online learning systems. And yes, it could be an intentional attack as well. Right. Right. So question from Tanmay is that in Twitter feed, we have a fake tweet. So how do we figure it out? So the moment you get such data, your model is going to give really awkward results, right? You have to be careful about those. You need to trigger alerts in those cases. And as your model is giving really um, bad results, you need to reevaluate what's going wrong. Yes, a lot of monitoring can be automated. So we basically need to keep eye on our production system, keep logs, keep alerts, keep events, and those kind of things. Or have every day, have your system send you an email in case it is giving the results below certain threshold. Okay, and you need to reevaluate. Okay, a lot of it is should be done and is done manually. And if you can figure out a pattern, or you can delegate it to Amazon Turk or some other set of people, then that could also be a good idea. So yeah, question from Ross. Yeah, bot detection tool is, yes, another hard problem to solve. But there are some libraries that help you detect the bots, but it's a decent decent problem to solve. It's a lot of people are trying to do that. There are many systems available today to defend against the fake traffic that you get, or the bots that you get on the website. Okay, but still it is quite hard. Okay. All right. So train your models on the regular basis using the fresh data. Automate the process of regularly updating of training models with fresh data. Otherwise, systems performance may fluctuate severely from time to time. And if your system is online learning, make sure to save the snapshot of its state at regular interval. So to keep on logging, keep on saving the snapshot of your model in case it's your online learning system. So that in case you are under attack using a bot or some other mechanism, you can roll back to the previous state. All right. So these are a few some of the things that you have to take care. And there is no straight away answer to most of the questions. These questions need to be dealt in a case by case manner. All right, so this is something that we drew last time. Okay, so much of the work that has been done in this session was in the data preparation steps. Then we spent a good amount of time in we basically have spent a lot of time in comparing the results. Okay, and the other time that would go in a production environment is building monitoring tools, setting up human evaluation pipelines, and automated regular modeling. Okay, and of course launching steps. Let me just put it here. It's kind of missed out. Data preparation and deploying. Okay, data preparation and deploying is two big steps in the whole process. Okay, so data preparation and deploying, yes, will take time, and these are the other things that need to be done. All right. So get yourself comfortable with the overall process. Know 3 or 4 algorithms rather than spend all your time exploring advanced algorithms and not spending enough time on overall process. Okay. So that is a very important point here. The important point is that the difference between one algorithm to another would be hardly, say, 2 to 3% or 4%, right? So it'll be really small. Okay, the difference between various algorithms performance is not too high. So instead of spending all of your time in exploring advanced algorithms, spend more time on automating your overall process and making the overall process strong, such as we talked about all kinds of steps that we have done in this course. You should not miss out on most of these, in your real project. Okay, and this is going to be, this is a very, very important point to understand, that the spend more time in the overall process instead of just exploring or trying to optimize a particular algorithm. Okay, because this is a very big tendency in most of the data scientists which I have met and worked with, that we kind of spend a lot of time in just studying all kinds of algorithms, and when we never deploy, we never take things to production. I mean, yes, this you will also notice in your personal experience. So but the more important part is the overall process. All right. So this is the rough sketch of things that we did in this session. We first studied the statistical inference. We also learned we learned about probability, measures of central tendency, and so on. And then we learned how to create machine learning model. So getting data, exploring data, splitting our data into test and training, and exploring different models and choosing the best one. So fine-tuning our model and presenting our solution. So these are the various things which we learned. Okay, presenting our solutions, we have not yet really created a presentation, but presenting our solution would be one of the steps. Okay, then we also learned about as part of the statistical inference and earlier, how to do stratified sampling. Then how did we visualize the data set? Remember, we plotted a graph on the map, and then we looked for the correlation in data. We tried to understand the correlation in the data. Then we did the data cleaning, right? So then we trained the model using scikit-learn and so on. Okay. So these are the some of the steps roughly followed in this course. All right. So this was pretty much about uh, okay. This was pretty much about the end-to-end project. We will be discussing about the various projects maybe in the next session. Okay. Okay. A question from Noor. Can you please brief us on how to present the solution? Okay. How? Okay. All right. So, all right. So when you're presenting the solution, I think a better way would be to have a sample ready. Okay. Okay. How to present the solution? I think a better thing I can do is get it in place, get you, okay. So I think this, I can do it probably at a later point of time. Okay. All right. Okay, a question from Tanmay. If we have to create the model in Python and then do the real stuff in big data, what should be the approach? Okay, let me try to see if I can answer this one. It's a really good question. All right, so here's the question. So a question is that whatever we did here in this case, let's say that this is not sufficient. This approach is not working in case our data is really big. Okay, so I mean, a very good question, and let me try to answer this. Okay, so in real, a lot of cases, what happens is your data is really big, and I mean, in many cases, what I found is that the raw data is really, really big. Okay, and you need to you need to you need to come up with the models on really humongous data. So in those cases, what happens is the raw data that we see here, raw data, in our case, in this particular case, the data was in few megabytes, but in real scenarios, let's take a case of the same example which I had talked earlier. The data was around 200 terabytes, the 200 terabytes, and so let me see if I can just quickly draw it. So these were the server logs, okay? Or if you think about, let's say, housing information, right? The housing data. Here, housing data was based on conducting the survey. Housing data was based on conducting the survey. But if, let's say, you're gathering lots of this information on the website, it could be based on the logs. So for me, the logs were close to, say, 200 TB, right? This was like few years data, okay? And here, what did we do is we basically used our standard big data tools, okay, such as MapReduce is what we did here. And it got actually reduced to a smaller size, right? A smaller set of data, okay? And so if the data is, say, bigger than 15 gigabytes or 10 gigabytes, then you will have to use some tools like big data or MapReduce. Okay. Otherwise, if your data is smaller, you don't generally need to go for many such tools. All right. And good news is that whatever process that we have followed, whatever pipeline process that we have followed, the same processes are available as part of MLlib. Okay. But going back on what we have discussed, so in many cases, if your data is really humongous, first part is getting the training data, or this will be a small sample. This will be a small sample of the overall data. This will be a small sample of the overall data, and we will learn and train our models here. Once we are done training here and it is working fine, then we can train a similar model or same model using tools like MLlib, in the production. Okay, so the point I'm trying to drive. Let me rephrase what I'm trying to drive. The point I'm trying to drive is all the time you basically measure if the problem can be solved using one machine or not. If it can be solved using one machine, solve it using one machine. Otherwise, if you think that if data is, say, bigger than 10 gigabytes or more, then you generally go for these distributed tools like Hadoop and Spark. Okay, Spark gives you MLlib. MLlib is designed exactly the way Scikit-learn is. So the way Scikit-learn has pipelines and other things, similarly, MLlib is designed. The way we have NumPy and Pandas data frame, MLlib also, Spark data frames provide you the similar functionality. Okay, so it is not very difficult to switch between the two. It's not very difficult. Here, in case of MLlib, we take the code to the data. In case of the local machines, the psychology is to bring data to the code. Okay, that's the biggest difference between big data tools and the local single machine tools. Now, um, at any point of time, you should be ready to move on to the bigger data. Earlier, it wasn't possible, but now it is very much possible. And in case problem you're trying to solve. In case there is no parallel tool available on say MLlib, say if you used one particular algorithm and that is not available on the MLlib, in those cases you can do it locally as well. Okay, so actually this is a huge subject. So there are two parts. One is there are multiple phases. One is analysis, right? Other is training, and third one is predicting, right? Predicting. So so yeah, predicting and data cleaning. Okay, so these are the bigger steps. Okay, and all of these steps can be performed either on the Hadoop ecosystem in the distributed fashion or locally. Okay, so generally this particular part, the analysis part, is something you basically sample a smaller data and do it on the local machine, while for the rest of it you do it on the production. Okay, whether you do it sorry, let me I'm using the wrong terms here. Okay, so for analysis, generally we do we have, let's say, huge data, and then we do, say, some kind of sampling and sampling, and then we feed it to the we basically we do the analysis of this data, and whatever models that we come up with, that whatever models that we have come up with after analysis, right? After analysis, whatever models we have come up with, we can take those models and either train on uh, do the training either on the bigger data or smaller data. Okay, and if your data on which you want to do the training, you can do it in the production. Okay, similarly, let me see. Actually, the flow chart is something that raw data, we need to do the data cleaning, and then so you can always combine all of these approaches. Okay. Okay, so let me take a further step back, and how can I best? So the sole idea that I'm trying to convey is that at any point of time, sometimes the analysis cannot be done locally. You might have to do the analysis on the server, on the Hadoop cluster, Spark cluster, or sometimes you have to do training. You can do training locally as well as on the cluster. Predictions, sometimes you can do locally, sometimes you might have to do on the cluster. Data cleaning, if the data is bigger, you will have to do it on the Hadoop cluster. Otherwise, you'll have to do it locally. So this one is mostly done on your machine, locally, while rest of these can be done on both. It's a function of how big is your data. How big is your data? And or you can basically combine the approaches between the two. Okay, so yeah, I think this how should I say? This is something requires a bigger analysis and a probably bigger example. So because most of you are not aware about, say, MLlib, so should we have a MLlib introduction towards the end? Towards the end. Okay. So we'll have, I think a better approach will be that I give you an MLlib overview, because MLlib is designed in the same way as scikit-learn, the pipelines and everything. So it'll be better to, give you a perspective on which functions are there in MLlib and how does it work? Okay, and we will also maybe mix the two approaches. Sometimes somewhere we'll take an example of the raw data, clean it using the Spark, and once we have the results, we can call the machine learning algorithms either locally or using MLlib or you by manually distributing things. Okay, I think we can take that example after I've given you a walkthrough of the MLlib. Okay, all right. Okay, so Gopinath's question is, it would be a good marketing for your Apache Spark course too. Yeah, that's right. That's right. But never, don't worry about that. The course keeps on selling. I mean, people, it's always overfull. I have to say no to many people in that course anyway. Okay, so, okay, yeah. There were a few more questions. There were question, our sample input of the raw data should be representative of large amount of data. Yes. So that's right, Tanmay. So in big data training done on population and normal database, we do on a sample. Not always, Anur. We generally do it on production. Generally do it on distributed. Okay. Not on the sample. But analysis, like the way whatever we learned about algorithms, right? That kind of thing we do it on the local systems. A question from Binta, data cleaning should be before training. Data cleaning should be before training. Yes, of course. It's just that order is not correct in this diagram. That's right, Gopi. If we do AWS Azure, we'll incur cost of training CTC. Yes, that's right. If you use AWS and Azure, and if your data is huge, the chances of getting huge bill is very high. Okay. Okay, a question from Noor. So there will be code change if big data is involved in production. Yes, there are slight code changes in your data pipeline of scikit-learn. There would be slight code changes. Yes. And of course, in the lucky for us that since we are operating on the data frame, right? Since we are our most of the processes are around data, correct? We split the data, we apply an algorithm on data, and so on, right? Therefore, making this kind of process parallel is very easy. Okay. Now we'll start the classification today itself. Okay. All right, so yeah, this was a good question, and this gave me quite a few ideas that I think I should do it, kind of show you instead of only telling you. Okay, so that was question from Tanma. Is there anything like unit testing concept in machine learning? So unit testing is there in almost everything. Okay, so whenever we are writing any function to do something, we generally write unit test for that. Like for example, if we wrote our own function to split something, we can write a unit test for the same thing. So the unit testing is there for any code, any piece of code. So there is no, we can't really ignore the unit testing in any of these parts. But in case of specifically for machine learning algorithm, a better idea, along with the unit testing, we generally keep this pipeline in place. Okay, pipeline in place. All right, good. Should we start just the brief introduction of the classification so that we are all on the same page? Just an overview. All right, so now you all are ready to start your end-to-end machine learning project, and our life as we go ahead will become really easy. And it's good that we were able to, do end to end before doing anything. We call it walking backwards approach, in which we start from an end objective and solve the problem going ahead. Similar thing we will do in case of classification. A bit of theory is kind of mandatory that we can't avoid. Most of you are comfortable with the theory already, so I'm going to go faster with the theory. And then what we're going to do is we are going to go with a problem. Here we are going to take the standard hello world problem called MNIST and then solve it. All right. So this is where we are. So it's the first thing that we are picking out of our whole chart of things. The first thing is supervised learning, right? Supervised learning, what was it? Supervised learning was where we have the data, training data. We have the training data having the information about what is right, what is wrong, and okay. So in this, classification is one of the kinds of problems. So classification, regression was the one which we used earlier, in which we had to predict the value, a decimal value or a number value. That was regression. But if we had to give an answer in terms of one of the objective type questions, like the way we have objective type question and subjective type questions, if our question is like an objective type, pick one of these. Is it true or false, or is it A, B, or C? That's classification. If we have to input a value, give the answer in the terms of that, what will be the value of this if these are the input parameters. In those cases, it's regression, and classification is basically identifying to which label something belongs to. So whether this image is 5 or not 5, this is classification. Or whether this is 7, this is 8, this is 2, this is 4, this is 3. Identifying the digits is a classification problem. So classification is the task of identifying to which category a new observation belongs. On the basis of observations whose category is known, basically we have the observations whose categories are known, and based on that we want to predict something. So for example, mails, spams, and viruses, we have a lot of stuff in our inbox, and our spam filter would um, put it in two buckets, either good email or spam. So this is called classification. Similarly, identifying which flower or which classifying flowers of a particular species is also a classification problem. This is called iris dataset. Okay, iris dataset is also a public dataset in which you have the images and the sizes of the stems and various other properties of the flowers, and we need to identify which flower it is. Similarly, classifying a credit card transaction as fraudulent or genuine is a classification problem. Face recognition is a classification problem. Okay, face recognition is a classification problem. The goal of this session is to classify handwritten digits. Okay, this is basically, there are two kinds of classification. One is called binary, other is called multi-class. Okay, so in case of binary classification, the answer is like yes and no. There are only two choices, and the classification is basically done between two classes. While in case of multi-class, there are many classes or many buckets or many labels which need to be applied on an input record. Okay, this is called multi-class. Okay, Yes. So binary classification seems like a decision tree, right? So now moving ahead, now the data set for our this project is MNIST dataset, Modified National Institute of Standards and Terminology. In this problem, we will use MNIST dataset. Basically, what is MNIST? MNIST is essentially 70,000 small images of digits handwritten by high school students and the employees of US Census Bureau, and along with what's written in them, digitized information, every every handwritten digit, there is a number, there is a actual number what this image belongs to. So that's MNIST dataset. So each image basically our data set is like this. There are 70,000 such images. Okay, 70,000 such images. So MNIST dataset problem is also called Hello World of Machine Learning. Whenever people come up with new algorithm, they test it on MNIST dataset to see how it performs. Okay, each image each image is in this data set, each image is basically 28 by 28 pixel. And here the interesting part is that each dot we are going to consider as feature. Okay, so it's a black and white image. It's a black and white image made up of these many pixels, 28 this side, 28 this side. Okay, essentially these many pixels. If we consider each pixel as a feature, so each pixel's value will be either on or off. Okay, so the input table is essentially having 7 at 84 columns with true or false value, as in 0 or 1. And in this data set, the total number of rows are 70,000. So the dimensions of the data set is 70,000 by 784. All right. So let's take a look at this in our sheet. Okay. All right. So you can check it out. I'm going to pull it again. Let me open my console. Okay, killing it. Let me kill the running. Okay, this can be killed. Okay, so the terminal is here. Now in this terminal, what we're going to do is I'm going to say cdml and git status. So it says that these both are modified. Instead, what I'll do is I will say git checkout, or I'll just copy it to my home folder, CP machine learning classification. I'll just copying my whatever changes I've made to separate places so that I can override it. Okay, so I'm going to say git checkout machine learning. Okay, and git pull origin. Checkout basically reverts the local changes from the local copy of the repository. And when I say git pull origin master, let me just see what is my branch locally. Git branch. Okay, I'm on the master, so I'm saying going to say git pull origin master. This time it's going to bring the repository from remote, and I think it'll be okay if I say git checkout machine learning. All right, so this has basically reverted entire changes back, and I've taken a backup of my work. All right, so let's open the classification. There is a file called classification.ipy notebook. Here, this one. Are you able to locate? Okay, so the first thing we are going to do is we're going to fetch the data. So from this, we imported an MNIST. Okay, so it's loading and downloading it. So MNIST is basically a dictionary. Okay, so we'll start from here and we'll observe our data set. Okay, so I think you can explore it during this day, and we can continue from here. All right, we can start from here. Bye bye. Have a good day. So thank you, everyone. We'll continue from here. All right. Sure, sure. We'll share the link for the new presentation. It will be made available in the LMS itself. Okay. So thank you, Balaji. Thank you, Bintao. Thank you, Gizi. Thank you, Gopinath. Thank you, Kamal. Thank you, Nirav. Thank you, Noor. Thank you, Prateek. Thank you, Ross. Thank you, Shahrukh. Thank you, Tanmay. Thank you, Abhinav. All right. Have a good day. I look forward to see you in the next session. Okay.